In this week's lab, we'll investigate the polarization of light. We'll focus on two types of polarization, linear and circular. Say you pick a point in space to look at the electric field of a light wave over time. Linearly polarized light has an electric field vector that always points along the same axis, but changes in amplitude at the frequency of the light wave. The electric field of circularly polarized light always has the same amplitude, but its direction rotates at the frequency of the light. We'll think a lot throughout this lab about how these two types of polarization are related. Remember that these types of polarization are special cases, which typically require special preparation. Most light sources produce unpolarized light, which can become partially polarized, for example, by reflection. So say you have a source of linearly polarized light. What can you do with it? One thing you can do is select a component of the light along some axis. This is what a polarizer does. The light you get out is linearly polarized along the axis of the polarizer. You could also turn the linear polarization into circular. This is done with a wave plate, which causes a time delay between two components of the light along different axes. The light you get out can be some combination of linear and circular depending on the orientation of the wave plate. Lastly, you could rotate the plane of linear polarization. This is done with a birefringent material, which causes a time delay between the right-handed and left-handed circular components of the linear polarization. When you add these circular components again after the birefringent material, you get a linear polarization at a new angle. So look at these three types of polarization optics in this lab: polarizers, wave plates, and birefringent materials. To do this, we'll use a polarimeter, which allows us to see the effect of these optics on a known linear polarization. Let's take a look at our equipment. Here's our polarimeter and a box containing the polarization optics we'll look at. The polarimeter uses a regular light bulb as a source of unpolarized light. Above it is a polarizing plate, so the light in between the bottom plate and the top plate is linearly polarized. The top plate, called the analyzer, is also a polarizer, which can rotate with respect to the bottom plate. So let's look at this from the top. As you rotate the analyzer, you can see that the intensity of light goes from a maximum to a minimum as its transmission axis rotates from parallel to perpendicular to the light's polarization. First, we'll look at polarizers. Take one of the polarizing films and put it in the polarimeter. As you rotate the polarizer, you'll see its effect on the transmission. If you rotate the analyzer so that it's not letting any of the light through, and then replace the polarizing film, you'll see that you now get light transmitted again. In this last part of the lab, we'll inspect a birefringent material. We'll use a biological sugar whose chiral properties cause left and right-handed circular polarizations to propagate at different speeds. When these components recombine after the material, the linear polarization lies along a rotated axis. This time delay corresponds to different fractions of a wavelength for different colors, so the final angle of polarization depends on color. Next, we'll take a look at wave plates. As you rotate a wave plate in the polarimeter, it will convert some of the incident linear polarization into circular. How much gets converted depends on the angle of the wave plate. When the orientation is set to convert all of the incident light to be circularly polarized, you'll see that the transmitted intensity no longer depends on the angle of the analyzer.